Right, welcome to part 2 of the exam style questions. And we're going to carry on just going through them. So this one wants you to do the experimental setup, include details of the apparatus, solutions, such and so forth. Move it to the side and let's do some drawing. So first of all, if we're going to do this, we need to start off with our voltmeter. So we've got a mark for the voltmeter straight away, so that's going to give us a mark. And then we'll do our lines, which is our wires. And then we need to do our electrodes. We need to decide what our electrodes are. So our electrodes are here. Right, do you see any solids? No, you don't, which means that this must need a platinum electrode. Oh, there's no solids again. Oh, we need a platinum electrode. So both of them are going to be platinum electrodes. So let's label that because you don't do drawings in chemistry. You do diagrams. So there you go, as you play platinum electrodes. We know they are both solutions, so let's draw our beakers. So we've drawn our beakers, then the liquid has to go above the beaker. Right, so we've got our liquids here. Now we need to decide which one's which. The anode is usually on the left, so basically our anode is here, and that is the negative electrode. So I'd always label it as negative as positive because, gets your marks. So the anode is where you lose electrons. Acid is the anode is where the current goes into the device. That's the device, so the electrons are going that way. So this loses electrons. We want the one that's losing electrons. Well, the one that's gaining electrons is the most positive, which is the most positive is 1.33, so that's going to gain the electrons. And that's going to lose. So the one that's going to lose is the iron. So that's going to be Fe3+ / Fe2+. So I'm putting in both parts just to be safe, because when I've got a solution, I tend to put in both the product and the reactants, Now, and you need to do that because normally you have the electrode is one of the reactants and then the solution. So if it's a solution, both need to go in there. As in the product and the reactants. So if we look at that, then we've got Cr2O7, and that means that goes over there. So that's going to be Cr2O7, 2 minus, and that's going to be H plus, and then we also have, you look down, Cr3 plus, and H2O. So we've written that. But would be good to put state symbols in there as well, but we know that these are all aqueous. So they're all aqueous. So let's just put AQ there just for completeness. And let's put AQ there, liquid there, and AQ there. Again, just for completeness. Now, salt bridge, we get a mark for our salt bridge. We have to label our salt bridge. Do not just put a line. Now, and we've got that. So in your answer, you should refer to the details of the apparatus. Well, I think we've done that, so that's all good. The solutions, yeah, I've done that. Standard conditions, we haven't done the standard conditions, So standard conditions is going to be 1 mole per decimeter cubed, and it's going to be 298 K, and it's going to be 100 kilopascals, or 100,000 pascals. So the question itself really is just going on about all of those, and you will get marks for all of these. Make sure your platinum metal's there because you've got your aqueous solutions, and you will be fine. 4 marks this will be in a normal exam. 4 quite simple marks, so good luck. So our next question is going to be the effect of changing concentration, and we're going to go exactly on about how you answer this in terms of the exam. Now we want to know what happens if the concentration of the silver ions, which is here, and the silver ions that are there, is decreased. So if we then do this, and I'll go a little bit lower here. If we then do this, you can see that we're not talking about manganate, we're talking about this one here. So that basically means I'm lowering the concentration of this, which means the equilibrium will go to the left. The equilibrium goes to the left, which means it loses more electrons. If it loses more electrons, this number goes down. If it gains more electrons, the number goes up. Loses more, it goes down. So that goes down. That means use this equation to calculate the overall E cell, and it asks you to talk about the electrode potential of the E cell potential. What happens to this number? That means, and this is the most negative, so this number here is going to get even smaller. So that 1.51 minus an even smaller number is going to give you a bigger E cell. Okay, so there's your two kind of points. The electrode potential of that becomes more negative, and the E cell becomes larger or more positive. Now let's talk about that in terms of equilibrium. Let's just say they changed it and used the word equilibrium in the question. So here we have, explain in terms of equilibrium why the cell potential increases if the concentration of Ag plus is reduced. So it's the same question, but we just changed it slightly. Now I've already answered it really. The equilibrium goes to the left. Okay. Now if the Ag plus concentration decreases, and normally it's set to 1, so it's less than 1, equilibrium shifts to the left. You get a mark for that. More electrons are released, so you need to talk about the electrons. It's releasing more electrons, there you go. Okay, and the cell has a bigger difference, and that's why the cell has a bigger difference in E. Now again, it's not telling you the cell potential gets larger, it's saying it's a bigger difference between them, okay? So make sure, exam technique, if you're ever asked about equilibrium like that, these 3 points are mentioned. Okay, our next one is an aqueous solution of iron 2 iodide. Okay, so you've got iron and iodide in there. Is mixed with acidified solution containing chromate 6. Now here's your chromate 6, that's chromate 6 right there. They've given you the two equations, okay? Right, so they want you to tell me what products you're going to get. So let's put that to the side, okay, and start looking at it. So I've added an equation here to give you an idea of what's going on as well. And you can see it's got Fe in it as well. So if you look here, the most positive one is the chromate, which means it's going to gain electrons. Now, as a result, the chromate is going to be reduced, which means it's going to make this. So one of your products has got to be Cr3 plus some water. Okay? That means the other two are going to lose electrons. Okay? The equilibrium of that one's going to go to the right, the equilibrium of this one's going to go to the left, it's going to lose. So you're going to make iodine. And this Fe2 plus, because it says iron 2 iodide, okay, is going to go that way. So you're going to make Fe3 plus. So the 3 things you're going to make, or 4 things you're going to make really, is the chromium, the water, the iodine, and the Fe3 plus. And we've been nice here just giving you the colour of the green, the Fe3 plus, okay, and the chromium is green. Now the iodine is also kind of brown in an aqueous solution as well, so you wouldn't see it. Anyway, that is how you do it. The first, name the products of this reaction. You normally get 1 mark for each. So this is going to be a very quick part, so this is for you to make notes really. They do sometimes ask you to define the term standard electrode potential, and it just throws people sometimes, okay? So I thought I would go over it in one of these. It's just the EMF, electromotive force, or the potential difference, or the voltage, or anything like that, connected to a standard hydrogen electrode. All right, that is your standard electrode potential definition, and it is often missed out. Now, you can also put standard done at standard conditions, and that would be important. Okay, so going over your standard conditions is important too. So 298 K, 1 mole per decimeter cubed, 100 kilopascals. So remember, whenever you use the word standard, you've got to talk about standard conditions, and standard electrode potential, the definition, is here. So we're now going to see about calculating a missing electrode potential. So we have the electrode potential for the aluminium redox system, this one, okay, and we have it for the overall. So these two added together, we have this. So we're missing the oxygen one, and we have to calculate the oxygen one. Now, this normally throws people. Okay, normally they do struggle with this, and once I show you, you'll think it's really, really simple. So let's put this to the side and bring that up. Okay, so first of all, it's how it's written. So if you look here, I'm losing electrons at the top. I'm gaining electrons at the bottom, which means the most positive cell potential gains electrons. The most negative one loses electrons. So basically, in our calculation here, this is the lower number, this is the bigger number. We know the bigger number is going to be applied to the aluminium. So it says here in the question that the aluminium one is minus 2.31. Okay, so basically we've got losing electrons here, which will be the anode, gaining electrons here, which will be the cathode. Okay, so all you have to do is plug the numbers in. So let's plug the numbers in here. Okay, we know overall it's 2.71. Okay, so it's 2.71 equal the most positive one. Well, we've got the most negative one because we've got the one that loses electrons, which is minus. So it's x minus, and if I look over there, 2.31. Minus a minus is a plus. Okay, so minus a minus is a plus, which means that you can rearrange that and you can say, right, okay, 2.71. I'm going to try and fit it in here. 2.71 minus 2.31 equals, and I think I can, 0.4. Okay, so my final answer is 0.4. All right, but again, if you get this question again, look at the equations, look at which one's losing, look at which one's gaining, okay? And there'll always be a hint in the question as to which one is which. So we're now going to go on to explain the products when you have multiple different equations, okay, that can interact with each other in slightly different ways because of their electrode potentials. So it says here that you can make FeI2, FeCl2, FeBr2, you can make all of those from Fe and these halogens. Those halogens are at the bottom here, you can see them at the bottom here, and Fe is at the top here. So you're looking at this electrode potential versus these electrode potentials, and we'll do that in a second. It then continues to form FeCl3, FeBr3, and FeI3. Okay, so this is now turning from Fe2 plus up here, so it's Fe2 plus because there's 2 chlorines, and it's turning into Fe3 plus down here because there's 3 bromines, okay? So on this one, we're looking at this equation here, which is Fe2 plus going to Fe3 plus, and again, all of the halogens. So we'll do that now, and there's quite a lot of writing in this, but again, it's there to show you how it works. Okay, so the first thing is we're going to do the halogens forming the FeCl2, FeBr2, FeI2. Remember, it's Fe2 plus. So we're doing that equation, okay, and all of these. Now, if you look at the electrode potentials, the first thing you've got to do is compare the electrode potentials, and we've got all of those electrode potentials. Notice all of these are more positive than all of these, which means they will gain electrons and go from Br to Br minus, Cl2 to Cl minus, I2 to I minus. Okay, they're going to gain electrons. These are going to lose electrons, Fe going to Fe2 plus. So all the time, you're going to get Fe2 plus and the ions, which would add up to make these equations, okay, or these compounds. Now, just a little sentence to say that's true. So iron has more negative electrode potential than all the halogens, which means the iron loses and they all gain electrons. Okay, so all the halogens gain electrons. Okay, and the iron loses. You then go for the next one, which is the FeCl3, the Br3 and the I3. Okay, so if we look here, you've got these two. 0.77 is less than 1.36, less than 1.09. Now, we're talking about different electrode potentials now. So this is Fe2 plus going to Fe3 plus. Okay, so Fe2 plus, Fe3 plus is this one here, okay, which is 0.77. So we've got 0.77 here. Now, 77 is less positive than 1.36, 1.09, but 77 is more positive than the iodine, 0.54, which means on the first two, the chlorine will gain electrons, the bromine will gain electrons, and the iron will lose to go to Fe3 plus, which gets you your FeCl3 and your FeBr3, but your iron is more positive, so that will gain electrons. To gain electrons means it stays at Fe2 plus, it doesn't go to Fe3 plus, okay? And that will lose electrons, which means it produces iodine and doesn't produce iodide. And to make all of these, you need the halides, the iodides, the chlorides, the bromides, and you need the charge on the iron. Okay, so that basically means Fe2 plus loses electrons for the reaction with bromine and chlorine, so it forms that. Okay, it forms that, but it does not react with iodine as it has a higher electrode potential, so it will not lose electrons, so it remains at Fe2 plus, creating just FeI2. Okay, so really, really difficult question, and you can see all the marks that are planned out all the way through, okay, and what you've got to do. So you've got to do comparison of electrode potentials, you've got to do then you've got to make a statement about that and a conclusion. So make sure you get these kind of questions spot on correct.